Hello everyone, good afternoon. This is Dr. Halapagajira. In this session, we are going to discuss how to design coaxial profit rectangular microstrip patch antenna using RT-derived dielectric material with a dielectric constant of 2.2 with a substrate thickness of 1.6 mm. All the input and output dimensions as given in this particular slide. You can go through that.
Hello everyone. Please watch, like and share it. Don't forget to subscribe.
Let us go to the HFSS platform by inserting the HFSS design. This is the working platform of HFSS. Now let us design the dielectric material by considering the rectangular box. Now I am naming that as a substrate, and also I am assigning some particular material derived from the library, and then I am assigning some color for that, and again some transparency so that inside any object is there we can easily visible. So this is the substrate, but it is not in the exact position. Now I am putting that in the proper position, that is minus 25.5 to minus 29 like that, and then I am assigning the z value where it is started, that is from 0 I am considering, and now I am assigning the length of the dielectric substrate, that is 51 mm, and then width of the dielectric substrate 59 mm. It has a thickness of 1.6 mm. Okay, and then if I see from the simulation, it is looking like this. This is the 3D view of dielectric material in the form of rectangular box. Now I have to save this file, save it, give some proper name for that, like extension.hfss, like that. Let us design a ground plane which is of rectangular in shape, and I am selecting the rectangular sheet and assigning as a ground plane name and some color. Again, these are all usual process in each and every model to solids. Now we have to put it in a proper position below the substrate. That's why I'm assigning these values, and z is 0 because it is at 0 level below the substrate. Now put it properly, and the length is 51 mm. Just see, substrate ground plane length is 51 mm, similar to substrate, and width is also 59. Oh, there is a height mismatch. I'll put it 0. Okay, wait. Put it 0, adjust this, and now you will get correctly it is placed. It is going to place. Okay, 0. Right. Now you can see the ground plane below the substrate, how it looks. This is the way, right? Ground plane, above that there is a substrate. And now it is also a conductor. We have to make unassignment into assignment. That means we have to assign perfect boundary for that along with infinite condition. Now the next process is select the patch, design the patch. Let us consider rectangular sheet and name it as a patch. It is also a conductor, and then by adjusting its position and everything, patch. Now put it patch, assign some color for this, put some color, and then transparency as usual. Okay, now put it in a proper position at the center of the substrate. X, Y, Z you have to put it here. Z is equal to 1.6 because it is above the substrate, and then patch length patch length is up 41 mm, and patch width is 49 mm. Just see how it looks. So there is some mistake here, numbering XYZ. Okay, adjust that. Okay, YY. Okay, now I'm changing that and see how the patch looks like in the simulator. Okay, it is exactly above the substrate at the center of the dielectric material. Now see, this is the patch above the substrate. Now assign that into perfect electric boundary. For that, select the patch and right click on that assign boundary as a perfect electric conductor. Assign boundary. That is perfect. We have to make hole in the ground plane to put the probe. Let us do that. Let us consider circular sheet and then name it as a ground plane cut. Assign some color similar to ground plane and now adjust the position, that is by xyz probe position, that is -9, 0, 0, and I am considering the radius as 2.0125 mm, that is standard. Then click OK. You can find the position where it is now. Just see, I am showing. Now select the ground plane and then select the circular sheet and then subtract, so you will get the cut. See what I am doing? Cut. Okay, this is the ground plane cut. Now we have to make hole in the substrate. That's why again you select not sheet like this. You select cylinder, circular cylinder, because it has its own thickness of 1.6 mm. Okay, cancel it. Select the cylinder. Here solid cylinder. I am taking that now. Drag and drop here and now assign the name, that is called SUB cut, substrate cut, and then assign the material, that is RT Duride, and now you just adjust the position like -9 mm, 0, 0, and I am cutting only a small radius of 0.6375 mm to pass the probe pin, and height is 1.6 mm. Now see how it is very small, so it looks like this. Just see. Again same way, you select the substrate and then this cut and go to subtract each other, so that you can find the hole which is made in the substrate. I'll enlarge and I'll show you. Wait. So this is the way we can get the cuttings, that means hole inside the substrate in HFSS. Okay, so now we want to make outer coax by using PEC material and placing below the ground plane. Make it as outer coax. Select the substrate like PEC material, PEC, perfect electric conductor, and then assign some color similar to conductor like patch. And then it OK. And assign the position, that is like probe position -9, 0 and -2 mm, because it is below the ground plane, and we are maintaining the length of 2 mm conductor, so put it radius 2.5 mm, and then I am putting the height of that conductor is 2 mm, so it is exactly settled below the ground plane. Just I'll show you. This is the way. Okay, I want to remove the central portion of the PEC material. Again I am selecting the same thing and I am pasting here, and I am reducing the radius. Instead of 2.5 I am putting now 2.0125, so that I can subtract this by the outer coax. Select the radius 2.0125. just see, it is smaller than the previous one. Now I am subtracting outer coax from my outer coax. Just see like this. See, this is the outer conductor of the coax probe, right? This is. Now I want to put another dielectric material in this particular portion, because it should not make a contact between inner conductor and outer conductor. That's why I am selecting some material called Propeller here. I am naming as the Propeller. I am assigning, but it is not available in the library. That's why I am adding this material. Like there is an option to add the new material. Name it as Propeller. Put what is the characteristics like a dielectric constant to tan, delta and all. I have 1.9. No any other changes required for this material. Validate this one first. So it will see there. Now okay, it is available now in the library. Select it and color it. And its dimension, radius is of 2.0125 as we know. So that I am adjusting the position now. That is 2.0125. paste it because I want to subtract. Here I am subtracting a small portion, that is 0.6375 mm, to pass the probe inside. That's why I am selecting the same material with 0.6375 mm, and height is same. So what I'll do, I'll select the outer this material, and then I'm selecting the smaller one, that is 0.6375 mm, whatever I did, and I'm subtracting again. Just see, if I tilt and show you, the Propeller material is filled inside with 0.6375 mm hole to place the coaxial probe pin. Let us design a probe pin. It will start from the base, that is -2, and it will touch the patch. Let us consider again cylindrical circular cylinder with a radius of 0.6375 mm, that is probe pin, and then assign material like PEC and assign the color. Now put it in a proper position by adjusting the dimensions and XYZ position. Anyway, it is started from -2, X is -9, Y is 0, Z is -2 because it will start from the base. Put the radius 0.6375 mm, that is the probe pin radius. Height is 3.6 because from -2 it will start, 2 plus 1.6 substrate height, 3.6, so that it will touch the patch. Just see, this is the way it looks, and it will touch from the base and to the patch. Okay, so now we have modeled all the parts of your probe-fed rectangular microstrip patch. Now again there are some process that we have to do. Let us do that. See how the probe and other parts of probe-fed rectangular microstrip patch antenna looks in the simulator. Just see. So this is the way we are doing that. Now for the simulation purpose, we have to put this in the air box, that is also called clean box. Let us consider a rectangular box which is placed from the above this particular patch and all. So I'll take as a radiation box and assigning some material like air. Okay, the dimensions, color, you put it some light color and make it more transparent because we can see all the inside parts. So now put the dimension. The length and width of this box is similar to ground plane, only the height will change here. Length is again -25.5, width is that is a 51 and 59. Okay, put it properly the position XYZ. It will start from -2, not from 0. Length is 51 mm and width is 59 mm. Length is 51 mm. Okay, and width is 59 mm. Height you have to take some 30 mm, 10 times of your total thickness of the RMPA. Okay, now it looks like this. So now what you have to do, we have to make this into some radiation boundary. That's why select all the faces, right? Select the faces, all the faces by selecting this option. Select all these 1, 2, all the faces except face towards the probe. Don't select that one. Now assign the boundary, radiation boundary. Now it will ask radiation. Okay, this is the appearance of assigned radiation boundary is assigned with this particular air box, right? Next process is we have to assign the port. We have to design a port. For that, select some circular sheet with a proper radius. Radius I am considering that as 2.0125. Again same color and all, 125 mm, and placing just below the probe 2.0125, and height nothing, that's okay. Right, like that. Okay, click on that. Just see where it is. It is exactly below the probe with a 2.0125 mm radius. I am considering this as a port. So now assign the port. Assign the port. Make it properly to appear this particular circular sheet. So just like this, you make it enlarge, and we have to see properly because we are going to assign the port, there are two types of port, wave port and lumper port. Normally we are assigning wave port because it is used here. Port, we put it name as port like that. Next, and then as a new line, you select from the center and extend that and touch the outer side, outer surface. Okay, it is telling that define, just see, defined. Now finish it. Okay, it will look like this. Just wait, I'll show you how it looks. This is the way how we can assign the port. The next process is we have to select the frequency sweep. Frequency sweep, here everything is fine except simulation setup, that we have to do by first initializing this simulation sweep, frequency sweep. Select resonating frequency 2.4 gigahertz and number of passes 20 here. Just put it OK, and then add frequency sweep, that is from 1 or maybe 2 to 3 I am taking, and step size is 0.01. I am considering this as a fast, like that. Okay, and then just OK it. Now assign the radiation boundary, that is also radiation sphere insert, that is 0, 90, 90, and then minus 180, plus 180, and 1 radiation for far field radiations. Just save it. Now everything is fine. See, all are okay. Now the next step is to analyze for getting the simulation results. Now I am clicking that, it is analyzing. In probe feed design, what happens, the position of the probe is very sensitive. We have to adjust properly, otherwise there may be some deviation in your results. It may shift very upper side or lower side, like that, maybe mismatching. We'll see what will happen in our case. I am explaining all the results, complete discussion in the next videos. Just I'll show you where it is going to resonate here, whether that resonance is proper or not. Just we'll see. Probe, why it is difficult here means the even probe may also behave like a monopole antenna. That is one more problem here. So anyway, we'll see whether it is resonating or not. Okay, it is perfectly resonating, but there is some small deviation towards lower side. That will check up what is the reason why it is. That I'll discuss all the results one by one in the upcoming videos. I think these discussion will help you all who are in the research as well as who are in the project, like engineering students or any technical master degree students. Definitely I think it will help. Just wait for further video of discussion of the simulation results. Thank you one and all.